Hello, this is Philip Myers of PEMY Consulting. In Module 1, we showed why the corrosion rate calculation methods in API 653 do not result in a corrosion rate, but rather the method is nothing more than an algorithm that can give you any corrosion rate you want depending on the repair to thickness. In this module, we'll show why the API 653 model is unlikely to be correct. But more importantly, we will show what can be done to mitigate the problems where it is a problem, which is not in a large part of that universe of tank inspection. Nonetheless, we feel obligated to point this issue out and give you the tools you need to protect yourself in those cases where you could get a tank bottom leak as a result of the API 653 algorithm. What we have here is a representation. The black rectangle is a section of the tank bottom, and time is going from left to right. Corrosion is going from the top surface downward. This red point represents the deepest corrosion in the tank bottom at the time the tank is internally inspected. If you were to draw a line like this gray line through that red point, the slope would represent the corrosion rate. That is, it would represent the standard linear corrosion rate. Recapping what we did in the last video, you can see that the red line is really the API 653 method that bases the corrosion rate on the repair to thickness, this red dot. That is the assigned thickness such that any corrosion that exceeds this red dot is repaired. And you'll notice that all API 653 corrosion rates resulting from this method are less than the linear corrosion rate model. You can draw this to the extreme and ridiculous conclusion that corrosion rates could be made zero if you were to repair the tank bottom to the original nominal thickness. This is another view of corrosion. This is the tank bottom with various thin spots and pits. X sub I, Y sub I is the deepest corrosion, and if you compute the corrosion rate based on that, you get the standard linear corrosion rate. The XJ, YJ represents every other thin spot, and you can see that it's variable depending on what those thin spots are. So to limit corrosion, you simply change the repair to thickness and make this slope, the corrosion rate, anything that you want. So in challenging the assumptions of API 653, we'll note that you can get a 20-year life regardless of what the previous corroded condition of the tank was. That doesn't really square with common sense. We also think that corrosion is not a deterministic process as shown by the previous slide, but it's really a random process, a stochastic process. Now here is the linear corrosion rate model. The y-axis is depth of corrosion going up, and the x-axis is time. The standard linear model based on the deepest corrosion is just this line. You can see that the API 653, depending on the repair to thickness, changes the corrosion rate anywhere from the linear rate all the way to the absurd value of 0. But what's important is there is a region of safety when you're above this dotted line, and that's most of the cases. In fact, that's why API 653 works as well as it does. But there is a niche of danger, which is when you are below this dotted line. This is the lower bound. We call this the bounded corrosion rate, and this is something that should be checked in your tank inspection programs to make sure you're not using corrosion rates, regardless of what repair to thickness you used, that are less than this bounded corrosion. To show this graphically, here is the standard linear corrosion rate based on the deepest thickness. You're supposed to take the tank out of service. In other words, you set the internal inspection interval from here, time equals 0, out to the intended length of time that that tank is going to be in service. When corrosion hits the green dotted line, which is the minimum required thickness, that's a rule in API 653. It serves as a safety factor, so you hope you don't penetrate through the tank wall thickness. If you were to let corrosion go on for this amount of time, you would penetrate the tank bottom. Here's a 653 methodology with the reduced corrosion or lower slope. And in this case, everything is good because even though you've gone past the MRT, you're here, which as long as you're not down in the black line here, you're fine. You haven't penetrated the tank bottom at the time of the next internal inspection. Now this case of the green line is the bounded case where you're safe as long as you don't let your corrosion rate get less than this green line. Because at this point, the linear model says that you would have just penetrated the tank here, and here the green is the computed interval from here to take the tank out of service. So this is the point beyond which you should never allow the corrosion rate to get less than. We have come up at PEMY with a simple formula. It's derived in white papers on our website, but basically it's this. The bounded corrosion rate is equal to 1 minus the minimum remaining thickness divided by the repair to thickness. Now this A stands for after repairs. So if this was 100 mils, a typical value for MRT, and you repaired to 200 mils, this would be 0.5, and inside the parenthesis you'd have 1 minus 0.5 is 0.5 times C, which is the standard linear corrosion rate. As long as you don't get less than this value, you're good. If you exceed it, then what happens is graphically shown here. The tank is corroding and finally is penetrated by corrosion under the linear model. This time period is a time when the tank is leaking. It has a hole in it until it is internally inspected, because this purple dot represents the point at which you would take the tank out of service under the 653 rules. So we have two models out there. One of them is a 653 model, and it's really dependent on many assumptions that are not realistic, like the previous slide that I showed for thin spots in a tank bottom. But more importantly, it's not a function of the condition or past corrosion. That doesn't matter. What matters is the repair to thickness, and that should challenge common sense. On the other hand, the standard model doesn't depend on any assumptions. Now, it's true that corrosion is not necessarily linear. We know that it's not, but it's a good enough assumption for tank bottom work. But it doesn't depend on a lot of assumptions like the 653 model does, and more importantly, it gives you a unique corrosion rate that is dependent on the tank corrosion history. So where do we go from here? Well, our website has a spreadsheet that you can download and play with that goes through the numeric examples that'll be shown in Module 3 next. But in order to convince yourself that what's being said is correct or incorrect, you probably should play with a spreadsheet and think about the problem more so that you convince yourself of whether or not this is an issue. Thank you.